Hello everyone, welcome back to Feed Technologies. So in today's video, I'm trying to respond to many requests that has been put in the comments section about the Python code, right? So for example, this one, micromechanics of composite materials. Here I try to do homogenization to average the stress over a volume over a body by taking stresses from each integration point and then multiply by its volume and then do it for all the elements and all integration points and then try to divide by the total volume, which will tell you the average stress over the body. And many people requested such as this request, they want the Python script. Can you please send me email? I cannot send you the code directly because this is related to a third party project. So basically, it's confidential. But of course, I can teach you how to develop one. So in today's video, I'm going to make a series of videos. First, I will introduce you how to use Python in Abaqus, like the basic function, how it works. And the second part is that I'm going to use the Python, modify the basic Python script from the Abacus to make function like looping and so on. And the third one is that I'm going to make homogenization. So we will make together. So I hope this video will be useful for you. So now let's start. So first open your Abacus. I'm going to be a little bit slow down because I want to make sure that my English speaking will be clear to everybody because I'm not a native English speaker and my and many people do not understand my English because it's not really clear sometimes. So bear with me. So click here with standard and explicit model, and first let's set up the working directory. Set work directory here, click, and then you browse to the folder that you plan to use. In my case, I'm using the desktop user. Where is it? Desktop and Python scripting. Okay, and then click OK, and then you type Control S. So save it there. Python intro. Okay, let me check my OBS first. Oops. Yep, it's okay now. So if you save it, you will have these two files. This is the CAE file, this is the journal file. So the journal file is the journaling file, the file that will record every comment that you press, that you execute in Abacus. So every time you click a button here, basically Abacus will record that comment in the journal file. So and this journal file is written in Python language. So this is the language that we have to copy. So let's make the backup, the one that we will modify here. So Python intro.py. So I just changed the extension, the format .py. So it's a Python file. Okay. Now open it, both of them, using the text editor that you like. I'm here using Edit with Notepad. So this is my Python. Now it's empty, still empty, because I don't have anything. I didn't click any button yet. So open two of them. So put it here. So the top one is the one that is going to be modified by Abaqus, and the lower one is my own file, the one that I will modify myself. Okay, so now let's make a very simple model. My model will be a circular model, a circular specimen, and then we are going to apply compression loading. In this case, I will create part, a 3D part, deformable, solid, extrusion, and then I will click here in the center. Here I am clicking here. If you see here, this is the coordinate. This is 0, 0.0, and I want to make 0 minus 10. So the radius will be 10 millimeters. I'm using millimeter here, okay? And then you click here, you click done. And then the depth, I want to make the depth 20. So this is the part, okay? So if we come back to the file here, he wants to reload it. Why? Because Abaqus modified the file, so it has a newer file. So you click yes, and then they will load all the comments that Abaqus recently execute, and my file is still empty. So what you need to do is to copy this comment. This is I'm not a Python expert, honestly. I learned Python just to finish my homework and just to finish my Abaqus work. So I'm not really very expert on it. So, but you need this. So it is to import several important features from the Abaqus. So here is the real part where where it is related to the Abaqus execution. For example, this one here. So let me tell you a little bit about this code. So the MDB model constraint sketch seed size 200. It's basically preparing the sketch, and seed size here is just to prepare the grid for the sketching. So if you remember, we just sketch it, right? And there's a seed size 200, and then the sketches here, it's basically what you wrote, what you draw, what you sketch. Here I just made a circle sketch, and then I define the center and then the perimeter. So the center is at point 0, 0, and the perimeter or the radius, I click at 0 point minus 10. You might remember it, right? Yeah, so basically in the Abaqus Python scripting, you can always change this uh, as variables. If you want, you can change x center 0, 0, y center 0, 0, and then you can put point my point x 0, 0, my point y minus 10, 0. So basically, if you want, you can replace it in here. Y center, and then here my point x is here, my point y it's here. So you can do it like that. You can change every number here into a variable. So basically, if you want to change it later, it's easier if you have it as a variable. So you don't need to change it manually. in the comment here, but you can just change the input file. You can automate how you create the part. For example, if I want to make the same part with a different name, for example, I call part name and I put part test. Okay, so here there is a name, and then they wrote it as a string here, but you can always change it to part name. Okay, so whatever you put here, they will create a new one. So part here, you can also change part name. Okay, so now imagine the depth. You can also change the depth. My depth, let's say my depth is 30, and then I can make 30. No, I need to change to my depth. Sorry. So basically, you just change the variable, not the variable. You just change the number, the fixed number, into a variable. So later you can change the variable as you want, right? For example, here, if I want to make a new part, I change the part name, and then I just copy here this guy, and I go to my Abaqus, and I will paste here. So there are two parts here. The first one is just basically the place to tell you the status of what you just made. A new model created. You cannot do anything here. It's just like a window to show you the latest things that you do. This one is called CLI, command line interpreter. So basically you can type Python script here. For example, here I already copy the script from here, from this one, and then I copied here. The name 3D is not defined. Oh yeah, you need make sure you need to copy all of this. Okay, yep, now it works. Now it automatically create another part called part test with the size that defined by you. Okay, but when you do that, actually you execute a new command to here, so Abaqus will write a new journal file to you, right? This is the previous one. So if you click save here, the Abaqus will notify you to upload or to reload the new Python journal. If you click yes, it's getting longer because there is one part, the original part, and the second part is the part that I just showed to you, the part test. So now imagine you want to recreate it again from the beginning. Just remove it, delete, and then you can close it if you want. Now let's open the command window here, and then you click Abaqus CAE. It will automatically open directly the Abaqus from this. And then imagine you want to repeat again from the beginning. You don't need to do that by clicking everything. Just simply copy paste our code here. So you see we have the part test. Now everything set. So this is how you create a part. Okay, so now the next step is to create properties. So when you move to properties, then when you create materials, actually in the background they will also create a new journal file. They will update your journal file. So let's do it first. Elasticity. Imagine you want to have a Young modulus of, I don't know, 220,000 MPa. The Poisson ratio is 0.3, for example. And then you click plasticity. Imagine you want to use fluorescence, so you click here plastic. So imagine this is steel, right? So at 500 MPa, the strain is 0, so it's yielding at 500. And then at 600 MPa, it reached 1, so it's 100%. Imagine now the model is a bilinear model. So basically you have elasticity and then you have a straight line. How you call it? I forgot how to mention it in English. Uh, is not rigid plasticity. Rigid plasticity means no hardening. This one is linear hardening. Okay, you click OK, and then you save. You save to here. Okay, if you open it, the JNL file. Oops. So the one above is the one modified by Abaqus, and from here you see here. First, you create a material with name material 1, and here you create elastic, and here is plastic. And then this is the data point. In this case, I only have 2 data points for the plastic. That's why you only have 2. 1 here, comma, and 1 here. If you have 10, you need just to copy it 10 times, okay? So in our case, we want to get it, and then I hope that you can see it. Oh, let me zoom it, okay? Let me zoom it so it's easier for you to see. So let's copy it here, and then let's make a comment. Yeah, so it's like a hashtag. Code below is to create material elastic plastic, right? While code code below is to create cylindrical part. Okay, so this is the center of the cylindrical part. This is the point. Okay, the radius, right? You can also put here radius of cylinder. So if you change it, this value to a bigger one, the radius will be bigger. This is the radius, in fact, right? The depth is the length of the cylinder, right? This is the part name. Now we're creating materials here. Material 1, when you want to use elastic, this is the code. So MDB models, materials, elastic, and this is the table. This is the Young modulus. This is the Poisson ratio, and this is the plastic. This is 500. This is the data point. In this case, we only have 2 data points. So if you have, for example, another data point, you can just add it, right? Add new data points. Okay, now let's continue. I already create this. Then you want to create section. Section 1, homogeneous solid, continue. And then click OK. And then you want to assign it. Assign section. You click here, click done. This is set number 1, set 1. And then OK, click OK. Then you save it again. You open the 2 files. This one tells you to update it. Yeah, so this is the update. So this is the save as, means that I just press the save as, control S, and this is the new file, the new comments. First, it's create the solid section. The material is material number one that we just create above, and this is the section number one. Okay, and this is some property, no thickness, because it's homogeneous solid, right? If you use shell element, maybe you need to put the thickness here. The models, MDB models, parts, this is how to create the set. Yeah, so first you make the set, and then you assign the section to that set you just create. So basically, from the model one, take the part, name part test, and then you assign the section, right, to this region. The region is the set number one, set one. Section name is section one. So basically, you assign section one to the set one, and then that's why this guy, you need to also save this guy. Oops. So you can tell code below to create section and assign it. Okay, and then yeah, so yeah, okay, I hope it's clear. Now we just did two modules, right? The part module and the properties. Now we assemble them. It's easy, just one click, right? Create part independent. Okay, it's done. So you save it, and then you open again the two files, and then you copy here. So basically there are two steps. First, it creates the coordinate system of the assembly. It's a Cartesian coordinate, and then you create the instance, right? So yep, you just need to copy it. So code below to create assembly coordinate and instance. Okay, so we copy, that's it. Now let's continue again. So what you need to do actually to do all the steps that you're required to do, and then while you do that, you record the Python script, and then you will reuse the Python script. You can modify the Python script for later use. Okay, now let's do the interaction. No interaction here because we're going to use only one part. And then you create load. Yeah, the load would be easy in this case. We create boundary condition. So you click displacement rotation, continue, then you click the part that you want to select, click done, and then you U1, U2, U3. Okay, did I miss the step? I think I didn't make the step. Yeah, let's come back again. So we before interaction, we need to go to the step, create the step, static general, and then you can choose anything you want. If you want to turn on the nonlinear geometry, you can. Stabilization, yes, if you want. Take the default, and I really like usually to change this guy, and the initial make it smaller. You don't need actually because they're very simple, but I just choose it the non-default value so that the Abaqus will write the comments so you can see maximum 10. No, no, 0.1. Okay, click OK. So if you wrote like that, check it here. So here root assembly, displacement. We made a mistake here because we did it by we did it the displacement first. So let's do it like this. Copy this one because this is the one that creates static step. There is adaptive damping ratio here. There's initial increment 0.01, maximum increment, maximum number. So yeah, that's why I changed to non-default value. So Abaqus will show this feature here, the nonlinear geometry, right? So you copy it here. Unless you need it, you know how to do it now. Code below to create a step. All right, now it's nice. All right. I just want to tell you guys that sometimes when you press enter, they will have this thing. I mean, auto indentation, and this can cause problems. So that's why every time I try to delete it back, making sure there is no tab because the Python is tab sensitive, right? So click again, and now we want to change the field output. If you want, click here, you edit it. I usually like to use evenly spaced time interval, so I get the field output at the evenly spaced intervals. So here I want to get 100 interval. You can change if you want. If you want to get, for example, if you want to do homogenization, make sure that you always check this ifall, or in implicit you can use efall. So ifall is integration point volume. So the volume that is associated to the integration point that you calculate, okay? And sometimes you can do chord. For example, if you want to redraw the deform shape in another software, for example, Paraview or MATLAB, so you want to get the coordinate for the models, and then you want to use Python to read it, make sure you export the chord, okay? And then the failure, we don't have the failure here. Okay, that's it. Click OK, dismiss, and then you click history output. You want to do the same thing, evenly spaced 100, and then you click OK, and then we finish the module, the step module. Okay, you click save, Control S, and then you try to reopen it, reload it again. Yeah, here it is. This one is to request for the field output at at the evenly spaced time interval, and this one is for the history output. So you can copy it here to here. So I want to say code below to set field and history output at evenly spaced interval. Okay, click here. Okay, this is the code. Okay, and then after that we go to the load. There's no interaction. We go to load directly. You already create the load. So what we need to do basically just to copy the load here. Where was it? Here. You create root assembly. This is the faces. You create the set by choosing this face, right? So yeah, it's here. You create set by using face, and then you create displacement, and then you apply to this face, set one. You call it set one, right? Yeah, set one, and then you apply to here, set one. So all right, then you can paste here, and then you can command here, quote below to apply load and constraint. This is the load. Now let's make the constraint. You need to do it carefully, right? Because the code sometimes didn't work because you mishandle the tab. Create boundary condition, displacement rotation. This is set number 2. You choose the face, and then u1, u2, u3, and the uz negative 2. So it's the length is 20, and then I give 2 in the tensile direction because the z is here, right? So if I put 2 means it's compressing. I want to make tensile, so I give -2 in this case. Oops, and I made a mistake. It should be in the z. Okay, and then you click save. Again, let's copy it again. So you create the faces, you call it set number 2, and then to this set number 2 you give this. You see here, first when I set the displacement, I made a mistake. I call u2 is -2, and then I try to change the value. I say u2 equals 0, and then u3 is -2. Now I fix it. So I can simply copy paste the three of them, but my code will not be smooth or clean. So instead of doing that, I just simply modify it here. I choose here -2 here, and now I just need to copy these two. I don't need to copy this one. Okay, and this is the okay. So I make the load and then the mesh. Now the mesh, the only thing you need to do is first you create sit instance. Okay, like this. Oh, it should be in the part instance. So you go to the part, you go here, sit part, and then you put number. For example, in this case 1.0. Click done, and then you click mesh part. Yes, all right. And then if you want to assign the type of elements, you go here, assign mesh controls. You want to make sure that this is hex. There's no hex dominated, okay? Because you want all of the element hexahedral. And then assign element type here. You click here, done. And then make sure that 3D stress standard linear, and then using second order accuracy. I'm usually using enhanced to prevent hourglass. Okay, if you want to element deletion, you click yes. Maximum degradation, it depends on what you want. Every time you do something, there will be a different output in the Python script in the journal file. Okay, click OK, and then click done. Then you click save, and then do it again, the same thing. Yeah, all right. So yeah, this is to make a sit part 0.1, right? The size is 1. And then this is to generate mesh, and then this is to set element type, and then yeah, that's it. So you copy 3 of them, you put the command code below to what, to generate mesh. Okay, so and then now the job, we don't need to do optimization. Job is to create my job. You click OK, and then you use parallel station if you want. Usually I'm using 4, let's say. I'm not sure if I can do GPU acceleration, but okay, it's like this one because I don't have GPU. And click OK, and then you submit. Okay, and then click Save. If you do that, let's wait until it finish. I hope it's not gonna take a long time. Yeah, so what we just need to do is to save the file, even it's not finished yet, and then open it again. You reload it again, and then you see that this is the last one, the one that create generate mesh, and then this one is to make the job. So this is to regenerate everything before you make the job, and this is the job, and then this is the submit button. The rest is uh, the message from the simulation, the running. You don't need that. You just click here to here. So you tell them code below to run to make a job and run. All right. So this is the basic idea of Python scripting in Abaqus. I hope you understand it. And let's see if it works. I hope it works. So now it's 50%. So let's check it. Yep. So in fact, it's working, even though it's not finished yet. So basically there's a thinning here, right? Here we have plasticity, and we made it manually, but we use the Python. So we record every Python commands that the journal file provides to us in a nice way, and then we can use it again later if we want to recreate the model. And I will show you how after it finish. All right, while we are waiting for the simulation to finish, let's modify a little bit this Python script. For example, in this job, we can actually make this job name as a variable, right? My job name.